Recording in progress.
All right, guys, so let's continue. So in this second half of today, this is basically now the last lecture. I will leave some minutes at the end of class today to just talk about project. Otherwise, because you're presenting, the next time we meet, you'll present your videos. Oh, by the way, so those presentations, let me stop the recording here. Right, so this semester, this course has been mainly about transfer learning, so it's a pretty advanced course. We use basically two tools, which were Fast AI and the Transformers module from Hugging Face, right? Transformer model was for mainly NLP so far, at least, and the Fast AI was mainly for image processing, mostly, right? And you guys use ResNet 32, so you basically use convolutional neural networks. So generally speaking, before transformers came around, which they came around in 2017 and then BERT, all that stuff after, the way that you thought about the two big areas of AI were image processing and natural language processing. So the way that you thought about those in the past was, okay, if it's image processing, it's CNNs. And if it's NLP, is something called recurrent neural networks. Transformers came and kind of displays recurrent neural networks, as we have seen all semester, or the second half of the semester. We use you use transformers for NLP. And then CNNs were being used for images. But as it turns out, people have started using transformers and started to think about how to apply them to images. Okay, so that's called actually transformers for computer vision or transformers for vision. So this is still an area that's very much, disputed, if you will, between CNNs and transformers for vision. So I'm just really going to, this is an area of research, so I'm only going to talk about it. We're not going to do any coding or anything like that, but it's the last idea that I want to leave in your minds, because the landscape is always changing, right? So I'm going to start with CNNs just to kind of give you the theory. So we use CNNs all semester through the Fast AI tool, but we never really looked at the architecture of it, right? So obviously the architecture I'm going to discuss today is going to be very simple, not like the ResNet 32, which is a much more complex architecture. So I'm going to go ahead, I'm going to use the book, my book from that I posted the link for. So let me just open Brightspace for this. And I'm going to open up the link. And remember, this could be on the exam, of course. So what we want to think about is, how could we adapt a transformer for image processing? But before that, since we're talking about vision, I'm going to talk about how CNNs work. Okay. And that kind of brings everything together, hopefully nicely. And, don't be surprised that you can also actually combine CNNs with transformers. So that's yet another possibility. All right, so I'm going to go ahead and start sharing the screen here. All right, you should all be seeing the screen. Click on content. I think I had added the book somewhere in here. Yeah, that's the whole book, I assume. Yeah. All right. So you guys should be seeing the book. All right. All right, so I'm just going to go to I think it's chapter 10 in this book. Chapter 6 then. All right, so here we are. All right, here we are. So all right, here we go. So we are basically, this last lecture, as I said, I'm talking about vision. And I'm going to start with, we did fast AI and we used resonance, so we use CNNs. But today I'm just going to talk a little bit about the theory of CNNs stand for convolutional neural networks. They have been traditionally been used for vision problems, image processing in general. And then now I'm going to end with this thought for you guys of, what are we going to do with convolutional neural networks? Do transformers modify things? Do they, do you combine them and make things even better? That kind of an idea. Okay. So I'll introduce a paper that you guys can read on your own, and then a blog post I found that I thought was really controversial but interesting. And there's two camps right now, people that believe that CNNs are done, and then there's others that think, no, CNNs can still. So they're afraid, right, that what happened to RNNs will happen to CNNs as well. So that's just, if anything, that's the idea for you guys to understand is that this is an evolving field, and you're constantly having lots of change. So before I begin, are there any questions? Nope. All right, so here the discussion is on convolutional neural networks. So this is, of course, a more advanced topic in neural nets. This type of technique has been used extensively for image processing. Okay, this technique has the capability to learn the features from the image data without human intervention. Okay, and so this is basically an extension of deep learning, but it has some additional layers. So you guys have a good understanding of deep learning, adding layers, etc. And this will just introduce, instead of a multiplication, a new operation called a convolution. And it also introduces new types, basically, of layers that you can now have in a neural net. Okay, so that's basically the idea. If you want to look at the code for this, you can go to GitHub, and just my website there. You can find quite a few examples of CNNs written from scratch that are very simple and aligned with this book. So the idea, of course, is here we're using images, so it helps to think about the MNIST data set just because we're familiar with MNIST, right? So I'm gonna go to the whiteboard here. I'm gonna lay out the problem a little bit. So a CNN is a type of neural net, right? So we got, some kind of a neural net, and we're still trying to do something like predict, classes, but the input is images, right? So, images of, cats, right? Or dogs or something like that. So let's take an image that is 28 by 28. Now remember, images can also be in black and white or in color. Remember, if it's in color, it's basically a cube that is going to be 28 by 28 by 3 versus a black and white image or grayscale, which is 28 by 28 by 1. Okay, so this is important, but at the end of the day, these are the inputs to the neural net. And then here, instead of just having regular layers, now we're going to have what are called convolutional layers. And you can have as many as you want. Usually the last layer before the outputs is just a normal feed forward layer. So this is just like the normal layer that you have used, but we have now these new called conv layers. So conv layer 1, conv layer 2, okay? And these layers are actually made up of 2 layers at least. So they're gonna have things in there. Now let me just give you the intuition of what CNNs are. So it used to be that like this was me, in 2011 or thereabouts. This is what we were learning. So there was no CNN. So what would you learn? You would learn that there's, maybe a multi-layer perceptron, right? And you have an image here. And it's an image of a cat, right? But it also has other stuff in it. There's a thing here and a thing there, and and there's like noise and things like that. So what you would usually do is that you would manually create these filters. Okay, so you would create these filters by hand, all kinds of filters called low pass filters, high pass filters, edge detection filters, segmentation filters. You have to literally learn blurring filters. So you would learn, for instance, let's say that you would build a filter like this. And what this filter does is that it's going to assign a value to the center pixel by looking at all the pixels around it and averaging them, right? So it would just look at all the pixels around them, take all those values, average them, and then that became the value there. So that was called a blurring filter. And that's just an example. You have to know, like, you have to know the numbers that would go in these filters. It was a requirement. So you would learn all these transformations, and then you would take the image and run it through that filter, run it through that filter, run it through that filter, all of that manually. Then you would aggregate or build individual networks for them. And then you would have a transformed image. So this is like the image. And then this would be the image transformed. And then that would go into, your basic neural net, right? So this would be your basic neural network here. And you would get the classes. Does this make sense, guys? So people made their entire living out of just creating these filters by hand. That was a very, that work took a long time. Like it would take a long time for somebody to come up with a new filter. And, there were complex things. Basically, you would take an image and then you would apply this filter kind of in that direction, right? Across the entire image until every pixel had been transformed. And this was, like if you were doing edge detection, right? So edge detection, it would, out of this cat, we would just get, the edges, something like, and that's it. That was the transformed image. So it would get rid of the noise and so on. So this, what I'm trying to state is that this was done manually. And then the neural net was here. Then some people created the convolutional neural network. And the idea was that the filters don't have to be learned beforehand. So you don't have to devise, I'm going to do an edge detection filter, a segmentation filter. And each one, by the way, has this algorithm. Instead, I'm just going to do this more efficiently. I'm going to build a neural network that does all of this together. What that means is that I build a structure where I just give it one image and the corresponding label, right? So this is going to be the one hot encoded, oops, this should be a 0. One hot encoded label. And I create the structure, which will have, I can have layers here, however many I want. So it can have however many layers I want, but the filters are going to be kind of part of the neural net. And you know what? I don't have to limit myself to just, 6 filters. Let's just say I want 32. Where does this number come from? I made it up. And then, it's just my, I want 32 filters. I don't know what they are either. You know, it's very much like when we do word embeddings, right? That we create these embeddings and we don't know what they mean. The filters were kind of the same idea. We don't know what they mean, but we just say, I want these filters. They're all connected, right? So what's going to happen is the image, let's say an image of a cat, has an associated label. Now this, of course, for this to work, you need lots of data. And it's supervised, so you need labels. So what would happen is that the image goes into all these filters, right, as you're training, and then you're going to be adjusting the weights of those filters, which is basically equivalent to learning the values that are here, right? And the operation is just what is called a convolution, which we'll talk about in a second. But basically, all these filters then will transform this image. They're all going to be different, and they transform the image into something else based on the filter. But remember, the values of the filters are initially random. So what's going to happen is, because you have labels, you're going to learn some interesting filters that are going to help with the classification. And as it turns out, the filters that they were ending up with are the same filters that we already had that we created manually. So we had filters like edge detection, blurring, you know, and all of those, plus some very interesting ones that had never been seen before. You know, things like cat ear detection and so on. All right, so then the 32 images, the 32 filters produce 32 images. Then these images are aggregated somehow, and they become the input to the next set of filters. And that's yet another, you know, another layer of filters that transforms the image. And then finally, once it comes out of the CNN, it goes to normal layers until the classification. But what's important here is, if you look in the past, the neural net or whatever the classifier was this. This was done manually by applying filters that are pre-known. You know, the values were already known, what they are, the operation. Whereas with CNNs, the filters, just the size of them is defined. So they're going to be like 5 by 5 or whatever it is, but you don't know the values. But because you have the input and the associated label, the filter weights are going to be learned automatically. In essence, that's the gist of CNNs. Does that make sense, guys? You guys understand that concept, that difference?
Yep.
All right, good. Yeah, so that's it. I mean, that's literally what a CNN is. That's how it works. And so the beauty of it, well, first of all, this displaced a lot of people, right? So all these people that were creating these filters, they were no longer needed because the CNNs will learn these on their own. All right, so that's basically the idea of a neural network, or sorry, of a convolutional neural network. So let's go back to the document here. So you can see, so the convolution defined, right? So, and CNNs. So what is a convolution, you might ask? So a convolution is a mathematical operation between two functions, f and g, to produce a new modified function, f asterisk g, which stands for f convolution g. So it is a special kind of operation that involves the multiplication of two input images with some additional conditions. So the best way to understand this is, you know, by looking at that analogy of the filters. So as an example, in image processing, this could mean the convolution between function g, which is an image, you know, a 2 by, let's say 28 by 28 image. So it's convoluted with a function f, which is a filter, where the filter is probably 5 by 5 or something along those lines. So what's going to happen in the operation is, you can think of it as the filter going through the image and transforming all the pixels. So this produces a new modified version of the image. You know, as I said, image processing uses filters to identify features in images, such as for edge detection. Edge detecting filters, for instance, look for areas in an image for high variation to identify edges. Now that is where the values of the pixels are all about the same, may be considered, for instance, background. but where the values are consistent and then start changing may mean that an edge is detected. So what that means is, in the past, when you were learning about edge detection, you would learn something like this. So imagine a person, right? And the person has hair, right? And so these pixels are going to be very varied, right? But then here is the background. And if you notice, as you're coming in from the background and you hit here, there's almost no variation here. And then there's a lot of variation here. So in the intersection of those two, that's an edge. So then you would say, oh, my edge detector basically will say, oh, this is an edge. And it was very simple just by looking at, you know, changes in variability. It would basically do that. And that was an algorithm that you had to apply. But that's no longer required because CNNs and can learn the filters automatically. So now in the past, you're aware that whenever we do deep learning, we do a lot of matrix multiplications of the X data times the weights W. Applying a filter to an image is a very similar process where you multiply, but in this case, you use what is called the convolution operation. So that's, it's going to be a built-in operation that we just use in a lot of the libraries. So it's going to be the convolution between the X, the image, and the filter, to calculate the weights, basically. In fact, there are many types of filters that could be defined for image processing. In the past, these filters have to be defined by human feature engineers, but the insight given by convolutional neural networks is that given training data with labels, these filters, the convolutional filters, can be learned by the model by learning the weights. And because the neural networks have multiple layers, convolutional filters learned from one layer can be used to transform inputs into for the following layer. So this is just an example of the architecture of a very, very simple convolutional neural network. So this is not ResNet by any means. This is just a very simple one. Just to kind of show how it works. So it'll be an overview of CNN for handwritten digits. The CNN we're going to use as our example consists of the following. It'll have an input layer, which is the image. It'll assume grayscale, and then it'll have two convolutional layers followed by a fully connected layer, which is just a normal neural net layer, and then the output layer. So here we can see now things that need to be clear when you define a CNN is the number of inputs, okay, and the size of each input. So for instance, each input refers to the size of the image. In the case of MNIST, the images are 28 by 28 each. The number of inputs refers to the number of channels for the image. So for instance, 1 channel for grayscale or 3 channels for RGB. And you guys know about color. The number of filters, this is going to be a value that the architect can define. There's really no specific reason, right? It can be, for example, 24 filters or 16 filters. These are convolutional filters, which will be applied to the images to transform them, basically. In the case of 16 filters, it means that 16 different filters would be applied to one input image to produce 16 new processed images. And then the new 16 processed versions of the input would be referred to as producing 16 output channels. The size of the filter is also defined. So for instance, 5 by 5, just like the image is 28 by 28. Then the number of outputs is going to be the number of channels that are going to be produced from layer to layer. You usually take those, let's say 16 outputs, and you're gonna average them or concatenate them somehow into one single input or output that becomes the input for the next set of filters. One important thing that also happens is one important note to be aware of is that the original input images don't retain the original size. So for instance, in the example of MNIST, which is 28 by 28, every time that the image goes through the convolutional layers, you're going to try to reduce the size of the image. And the idea there is you're trying to just keep the important things and get rid of the unimportant things, okay? So in this case, for instance, this is called downsampling. So the images are downsampled, and specifically in CNNs, this is called max pooling. So for instance, in our example, the images will be downsampled from the original 28 by 28 to 14 by 14 to 7 by 7. Okay. So let's think of now in terms of numbers of the following architecture. So we're going to look at the architecture for a simple CNN. It'll have the following characteristics. It'll have one input layer, two convolutional layers, one fully connected layer, and the output layer. The input layer will consist of images of 28 by 28 with one channel, so it's only grayscale. The first convolutional layer will have 16 filters. Each will be of size 5 by 5. This is just something you define as the architect. Given that it has 16 filters, its output will be 16 process images or 16 channels. And the images, all images will be downsampled from 28 by 28 to 14 by 14. These will be aggregated and will become the input to the next layer. All right, so usually like averaging them is the simplest thing. So then in the second convolutional layer, we will have 36 filters. These filters will be 5 by 5, and its output will be 36 processed images. So it'll take whatever the first convolutional layer produces, use that as the image, the transform image, and now run it through 36 filters and get 36 new images, new transformed images. So there's that scheme of how you aggregate can vary. All right, so there's various types. And then after this convolutional layer, notice that the images will be downsampled to 7 by 7. Finally, that is aggregated as well, and that will be connected to just a normal neural network layer, what is called a fully connected layer. In our example here, it'll have 1,024 neurons. This is just a normal layer that will connect the output of the second convolutional layer to the output layer itself. Because this is MNIST, of course, the output layer will have 10 neurons, which represent the classes basically that you're going to have available. Okay. Any questions so far, guys? Is this making sense? Guys, any questions?
No questions.
All right. Yeah. So just remember it's called convolution because it's performing. Convolution is a mathematical operation, and as I defined it, it's a transformation between two functions. In this case, two grids: the original image and the filter, and it produces a new one. But the operation is beyond a multiplication; it's something else. But the most intuitive way of understanding it is, like I said, just passing a filter through the image. So you can see here, for instance, our original image is 28 by 28 by 1. That gets passed. Notice here there are 16 filters. So the image gets processed by the 16 filters, and it produces a tensor that is 14 by 14 by 16, because 28 by 28 is downsampled to 14 by 14. Then the output of this tensor then will be processed by the 36 filters, and that will produce, at the end, an aggregated tensor of 7 by 7 by 36. And then notice this one is just a normal neural layer, pretty much like the ones we've been using. And then this is the class. So it's almost, in a sense, you could think of, if we're thinking now of transformers, you could almost think, well, let's just replace this whole convolutional section with a transformer, see what happens, or let's keep this, but here in between the convolutional section and the fully connected section, let us add a transformer, right? So remember that we're kind of tying this idea together. And so that's where the research is. People are trying this, and some people think that transformers will replace CNNs. So anyway, so that's kind of the idea. You can see here, this summarizes the architecture. And after this, if you want to read through, you know, this is the code of how to implement a CNN in TensorFlow. So definitely take a look at it if you'd like. So hopefully that gives you the overall idea of a CNN. So now let's go ahead and move to, so before I move on, I guess, was this clear enough? Are you guys, do you guys understand?
Yep.
All right, great. So now let's move on to the idea of transformers in vision, right? So let's make the connection. So for that, I'm gonna open up a couple of things. That I would recommend that you take a look at, especially, I don't know if you guys are working on vision problems or not, but if you are, certainly I want to recommend the following paper. It's a nice literature review. So it's called Transformers in Vision Survey. Obviously. Yeah, so you should be able to see it, I think. So here's the paper by Khan and et al. And we can click on the PDF. Pretty long paper, it's about 30 pages long, but it's fairly recent, from 2022. And so basically it goes through the history, so you can take a look at it, right? And then see how it lays out an idea. We have an image. You have to break it up into parts, right? And then key, Q, and V is the whole idea of attention mechanism. So somehow, you know, you're gonna pay attention to different sections of the image, very much like what you do with NLP. And so you add that in there. But we'll get into this a little bit. So just for now, you know, I'm just recommending the paper. Take a look at it. So this looked pretty complete to me. I'll talk, I think, actually about this one in particular. I kind of like that one because there are some different ideas on how to do this. Okay, so, but certainly you can read through the paper. And so this is very timely. So let's see, it's got some discussion here, some benchmarks, it seems. Okay. All right, so that's one thing that I wanted to point out. And then the other thing I wanted to point out is actually this blog that I found, Transformers in Computer Vision. And as you can see by this is from Towards Data Science, which is a pretty good blog. And as you can see, people like to make very bold statements. Farewell convolutions, right? So basically that whole thing that I explained to you, CNNs, which is not even 10 years old, some people are now, you know, bidding farewell to it. So that's an interesting thing. And this kind of just shows you how this field is, right? So if anything, hopefully you guys have taken some of these courses. If you like this stuff, my recommendation is just make sure you keep up, because you're already 2 years behind probably. And that's always how I view it. I'm always at least 2 years behind. All right. So this, you know, this is a nice blog. It kind of goes over some of the topics. I actually don't do much work in like image processing, but you know, you never know. So take a look at it. I think it's an okay-ish explanation. but they do have one of the particular scenarios I liked. This one, yeah. So the vision transformer VIT. So if you click on that, that'll take you to this paper, which I like this idea. I thought it was intuitive to understand. The paper was published in 2021. It's called "An Image is Worth 16 by 16 Words." Transformers for image recognition. This is from, of course, Google. As you can see, they're already doing work in that. And so it's worth taking a look. It does describe this mechanism, which is, I thought, was pretty intuitive. We'll take a look at it in a sec. Of course, Jean LeCun is there, as he was one of the original people for CNNs. Jean LeCun, by the way, who's the director of AI at Facebook, defends CNNs. So it's interesting to follow him and what he says about this whole idea. So anyway, this is a paper I would also recommend if you're doing it. It's certainly if you're doing image processing, I strongly recommend you read this, the survey one and this one, and the blog, so that you're not doing CNNs when you should be doing transformers for vision. Jason, like I remember, your project is vision, correct?
No.
Not vision? Oh, okay. I thought you were doing like
I would have liked to have done vision. I thought it was all NLP.
No. I mean, I don't mean your project in this class. I mean your like your directed project.
Partly, yeah. We have to use cameras to
So there's
control where our robot's going and stuff.
It's pictures are involved, right?
Yeah, for like what Wen Ling is trying to do in it.
Okay. Yeah, that's what I'm saying. So I remember, I don't know what Kyle, what are you doing for your directed project? Is it images?
No, it's like IoT traffic.
So it's network traffic, right?
Yeah.
Yeah. All right. Yeah, but and I don't know that Josh is doing it. But yeah, so my point is, if you're doing image processing, so I think this applies to Jason a little bit, certainly take a look at this paper and the survey paper because it's very timely.
Yeah,
right.
I was can I say something real quick?
Yeah, please. Yeah.
I was actually looking into something that's kind of a combination of our vision and the NLP, where basically through the computer vision. Okay, well, let me start over again. Robots will make a decision based on some type of sensor input, like heat or sound or whatever.
Right.
So this would be more along the lines of a robot making the decision based off of natural language that it sees and can read from its camera.
I see.
So it's a combination of both of them.
It's seeing labels or something, and it's like
exactly. Well, like, so if what you're showing right now on our screen was a sign on a wall, and the robot's vision can see the sign, then it can read it and turn it into text, and then make decisions based off of natural language processing.
Got it. Yeah. That's a very well established problem. I think you can get good accuracy on that one because especially if it's typed and not handwritten, right? So that's
right. Yeah, handwritten's much more difficult.
Yep. All right, but good. Yeah. So I just like I said, I'm wrapping up the semester, right? So it's only logical that I should wrap here. It's funny how progress in deep learning started with image processing and then it extended to other areas. Now transformers started in natural language processing and now it's going into images. So I find that, a little hilarious actually. Anyway, so yeah, read this paper in particular. I think it's a very important one. Read the blog and then read the survey paper. Oh, okay. Hold on. Where was that? And read the survey paper. Yeah, this one. if you're interested in like the state of the art in image processing, and just to see how it plays out. I don't, you know, we won't know for 3-4 years, or probably sooner, actually, in 2 years, we'll know if like CNNs are obsolete, basically, or if you need both, or you know, so it's not clear right now, to me at least. Anyway, the last topic I'm going to close with today is really this vision transformer. So it's based on this paper by Google. So you can see it's Google tried this. And so it's called a vision transformer, VIT. And you can see this model presents a new, so that just means state of the art on image recognition, with a model that even fully relying on self-attention is able to present performances on par with other, you know, CNNs probably. And if you look at it, the idea is actually quite kind of simple, right? If you look at this object here, if you look at this representation of this model, this should remind you of BERT. This is actually very similar to the BERT model. So if I go BERT, which is the pre-trained, you know, bidirectional transformers for language understanding, right? We covered this some weeks ago, I believe. And if we look here, yeah, this, right? I think I want to see if I have a better picture of this. Guess not. But we can use that one. So if you look at BERT, if you remember, BERT would take tokens, right? In one sentence or 2 sentences with a CLS tag and separators. Then it does all the encoder, and then it would encode the words, but also it had this class embedding. And this embedding was supposed to represent the context of the input. But this was in terms of NLP. Now, if you go to this paper over here by Google, the Vision Transformer, or VIT, notice this is pretty much the exact same thing. We have the transformer encoder architecture, just like BERT. Notice that that's this thing here. And notice that all it does is it takes something, normalizes it, it's got the multi-head attentions, it's got a normal layer, a multi-layer. So it's exactly the same layer. Notice that the output is almost the exact same as well. You got one token here. That's the embedding for the whole context. That's run through just a standard multi-layer perceptron. And then you have the class, like, oh, this is a bird, this is a ball, this is a car, right? You can see the class there. So that's, you know, if you look at this, if you look at it from, oh, let me see if I can do the annotation thing. I can probably do it. Let me annotate here, yeah, so I'll do that. So if you look at this one here, you look at like about there, right? That's very similar to if we go to here, right? It's almost the same thing. So I'm going to annotate it also. So here you can see the BERT model is pretty much the same. You've got some inputs going into the architecture, and then you've got this C class, right? And then here in the BERT transformer is passing through a multi-layer, and then it's predicting classes basically. So it's very much like BERT, you know, it's literally it. I mean, it hasn't changed at all. What changes, at least from what my understanding of it is, of what Google did is in, you know, it's here, right? In the inputs and how they do it. So if we go back to that paper, I'm stop this. All right, so if we go to this paper, what you can see here is that the inputs they have what are called linear projections of the flattened patches. So if you look here, they took an image, this image over here, right? So this is the image here, this image. they broke it up into pieces. Each one of these is called a patch. And notice that they're sequential, right? So they've got like this one is this one. So this one is this one, and this one is that one, and this one is this one, and so on all the way to the end. So there's the sequence. They provide that encoding. You know, this symbol here means the position encoding, right? So 0, 1, 2. Notice that this one is not tied to the image, and instead it's just going to be that CLS symbol, right? So it just means that's the class, feeds in, and then comes out here for the, but remember that what the transformer will do is it'll take all of this and it'll create a context, right? An embedding of the context of the whole thing. And so what's kind of nice about this is that you're treating now these little pieces the same way that you would treat words. So for instance, you know, just kind of to do an analogy, the cat is sleeping, right? So it's almost like I would say the cat is sleeping, right? So that's what they're doing basically. And so this almost translates to the cat is sleeping and so on, dot, dot, dot. And now this vector, which is probably, I think this is where that 16 by 16 comes in, feeds in through this layer. And this is a layer that will basically try to convert this into an embedding, you know, different kinds of embeddings, and then those embeddings will go in as inputs into the BERT model. That's basically it. And if you look, that's why the name of this paper, oops, sorry, I need to like get rid of that. The name of this paper is, you know, it's kind of in the name, right? An image is worth 16 by 16 words, right? So it's really, that's what it's doing. It's breaking the image into these patches and then treating them as the inputs that are going to get processed. Now, the fun thing about this is that these patches are the things that go into the attention mechanism. Remember, they don't go necessarily directly into it. You know, they'll probably go into that whole key QV projections, right? And those are the things that get compared in multiple ways, but you're just mapping this to those and then comparing. So what happens is, in a sense, is that these things are paying attention to each other somehow, right? So like, it might find that if I do this is just a crude example, but it might find that these are related and this one is related to that because there's sky, and then these two are related, and like windows are related there and there and there actually. So they get to pay attention to each other. So there's a little bit of learning going on there, okay? Now, obviously, adding convolutions is also a possibility kind of in the beginning. This is just all, you know, at this point, this paper is extremely new. So certainly, you know, it's kind of, we're at the beginning of something interesting. But it's a 2021 from June, so it's not even a year old. So we can read through the, you know, it's definitely Google research at the Brain Google team there. All right, so let's just read through the abstract really quick. So it says, while the transformer architecture has become the de facto standard for natural language processing tasks, its applications to computer vision remain limited. And think about it. This is as of 2021. So if you guys want to publish a paper, certainly using transformers would help you, especially if you're doing vision. In vision, attention is either applied in conjunction with convolutional networks or used to replace certain components of convolutional networks while keeping their overall structure in place. Google here that shows that this reliance on CNNs is not necessary, and a pure transformer applied directly to sequences of image patches can perform very well in image classification tasks. When pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks, such as ImageNet, Sci-Far 10, etc., the vision transformer attains excellent results compared to the state-of-the-art convolutional neural networks, while requiring substantially fewer computational resources to train, right? So you're leveraging, once again, that incredible power of GPUs that transformers leverage. Okay, so you can read through the rest of the paper. Here's the model overview. GELU is a new activation function. So if you guys remember ReLU, GELU is the new one that uses some ideas from Gaussian, the normal distribution, the Gauss function. So something also worth looking at. See, it talks about fine tuning also. And then here are the experiments. You can see they're running this on various benchmarks. There's a VIT base and large and huge. Okay, so that's hilarious. The number of parameters for huge is 632 million. So that's okay, pretty big. And then here it talks about, the approaches. Notice it's kind of leveraging just the BERT architecture. Here's, I assume, the performance of it in the various data sets. And then there's some talk about the pre-training requirements. Notice how the attention mechanism, just like before, remember how we were visualizing the attention mechanism on the words with those little links? Look at how interesting this is. The attention here is able to pay attention to just the dog, the plane, the leaf maybe. So that's really interesting too. Here's some visualization of filters. Yeah, so that's I think one of the nicest papers in this area. Certainly talks a little bit about the math and a little bit about the fine tuning, etc. You can take a look at that. But yeah, so that's like I said, this is something that I have not used, of course. But I wanted to kind of conclude the semester with this idea of how transformers are now being moved into the realm of vision, and it's certainly worth for you to take a look at that. All right, so that I'm going with that. That's it for content for today. So I'm going to stop the recording.